Hey everyone, we're back. Now we're gonna do example 4. It says an object from point A to point B as represented there. Point A, as you could see, has kinetic energy, it will be moving down. B will be potential energy. So A says what is the work done by N, the force of N. Yes, okay. So it will be represented as a force going up. So in this case, we're gonna multiply the surface by N. We're gonna multiply the surface by N. So it will be in this manner. Yes, this is a change. Delta is change. We will give a 0. Yes. So the N is always perpendicular to the vector displacement. Yes, in this case, would be let's get the object from the first mountain or the first hill. So the N is always perpendicular to the vector displacement. So in this case, we're gonna draw a little representation of how it will be moving. It will be moving here. Let's say it will be going from here all the way here, and it would have this too. Now we said perpendicular. Look, perpendicular. Yep. So therefore, no projection of N into the change of S. So therefore, work is 0. Yes. The N of the force is always perpendicular to the vector displacement. And this is true for all objects in that scenario. Yes. No projection of N into the change of S. So it will be 0. Yes, that will be for A. Now, what is the work done by F? The work done by F. So we're gonna take the possible forces, and we're going to see a little representation of the vertical displacement and mg. Now with these two, we're gonna plug it in with y1 and y2, 2 points, but those 2 points will be called y1, y2 because we don't have any special units that we had gotten. So we're gonna do this representation. We're gonna do mg going down, vertical displacement of S, of course, and then we're gonna do x and y, the change of x and the change in y. Yes. Okay, so W. Work. Work, we said it was 0 because of our sentence, our formulation of how the box will be moving and how it will be moving with the kinetic, and we will come to a slightly stop of potential. Okay, so we are going to do another thing or another. I'm gonna do 2 ways of doing this. So mg, we said it was going down, and that will be with the change in x. Now we're gonna do with the change of y, which both of them will be going at the same direction. Yes, so correct. So now there's a big influence of mg to y1 and y2. So 0, because of the representation, they're canceling each other, plus mg to y1, y2. Yes, that's it for part B. Now part C says, what is the speed at point B? Point B. Point B, here we say is potential. Okay, let's go. Okay, so we are saying we're gonna work with what we got. So as I was saying in the other examples, the work net is also equal to the change in kinetic energy. So we're gonna draw like this because we have the n and we have mg equals 0 plus mg. This was from our previous part B, and we get the net is equal to change of kinetic energy. Now we're going to influence these two. I'm going to put 1/2 mv squared. This will be v2 or y2. So, but in that case, it's v, which we're using because of velocity. So if y2 is 0, then we're gonna do this. So if y2 is 0, then we will represent it like this, mv. We represent it like this, like the same as this. So, but if b1 is 0, we gotta represent it like this. It's a must. We gotta do this. So mg of y1 to the half of mv2 to the 2. So v2 to the 2 is 2 gy to the 1. Now, to take away the squared, y. All right. Okay, we're gonna move on.